Well, welcome back to Math 221, everyone. As you know, we had the exam, depending on when you're watching this. If you're watching on the day that it goes up, you had the exam yesterday. Um, I'm actually recording this while you guys are taking the exams. So you're taking the exams, maybe right now as I'm recording this, but sometime today. I want to talk you through real quick sort of our schedule for the next little bit. Um, we have today's lecture where we're going to be largely focusing on the applications of the first derivative and sort of what it means right now that we've spent all of the last 2 weeks really looking at how to compute it. We can sort of take a look at what it means, right? Like what we can do with the first derivative. Um, and then we're going to continue to tell that story sort of through the week after, largely going through chapter 4 of the textbook. And then after that, we will turn our attention to exponential and logarithmic functions, and we'll spend about 2 weeks on that. So that's give or take our schedule for what's coming up. But with that in mind, let's take a look back at the first derivative. So we've used this example a little bit before. We've kind of touched on it. But if you take your typical car, right? The fuel economy of the car is going to look a little something like this, okay? And uh, according to the Department of Energy, this value right here is about 42 miles per hour. And this is a really important graph for a number of reasons. One, it tells us, if you're wanting to maximize fuel efficiency, well, that's how fast you should drive, right? This graph here is going to look a little bit different for every car, right? Some cars might do this, some cars might do that, but like this is the average, right? This is about what they're going to look like, right? And so we've said this point is 42 miles an hour. And what I want to draw your attention to is that here, right, our function is going up, right, as we increase the speed, right? Speed is here, and miles per gallon is there. Whereas over here, as we increase the speed, we decrease the miles per gallon, right? When you're over here, if you go faster, your output of your function, right, increases. Here, if you go faster, it decreases. Okay, and we're interested to seeing if we can sort of use these ideas, right, of increasing and decreasing to study other functions, right? And in order to do that, right, we do need a sort of formal definition for increasing and decreasing, right? Um, and those are going to look more or less exactly how you would expect, right? So we can take a function, f. We say that it's increasing on an interval AB um, if for all x1 and x2 in AB, right? So if I pick any two elements of this interval, right? Well, then f of x1 is less than f of x2 whenever x1 is less than x2, right? And this follows, again, pretty much exactly what you would think. And we can copy this definition and use almost an identical one for our concept of decreasing. I guess we'll just do that. And how will we need to change it, right? We'll need to say that a function is decreasing on an interval AB, if for all x1, x2 in AB, we can just swap this sign, right? And I guess I'll change this increasing to red as well, right? The pictures of these situations are pretty much exactly what you would expect, right? So we can grab some functions, say, like this. Say it looks like that, right? Say this is your A, this is your B, right? Then if I pick any 2 points, right, in this interval, say x1 and x2, whenever you have x1 is less than x2, you have f of x1 is less than f of x2, right? And the exact same story can be told right here, right? A, B, and then x1, x2, right? So here we're talking about a function increasing or decreasing on an interval, okay? And it would be helpful to us if we could dream up an idea of increasing or decreasing at a point, right? Rather than saying, well, on this whole interval, it's increasing, right? I mean, that is an incredibly useful thing, right? But what if we're interested more in sort of looking at the behavior of individual points, right? I'll just delete these annotations, right? What if we're curious, are we increasing or decreasing at this point, okay? And the natural way to extend this definition, right, is to say that we're increasing at that point if I can find an interval around it, right? You know, not every interval around this point is increasing, right? Say we were to take this interval, right? Well, we can kind of see we're decreasing here and we're increasing here. So the function is neither increasing nor decreasing on this interval, right? But surely I could pick a smaller one, right? And since I can find an interval around this orange point, right, around which it's continuous, we say that, you know, if we say that this green is, you know, y equals f of x, and this guy is f of c, right? If this is the situation, right, we say f is increasing at x equals c because I can find an interval around it, okay? And maybe your mind is starting to turn this way, right? But here's the thing I want you to notice. If you remember last week, and I believe we touched on it very, very briefly the week before, one of the things that calculus is doing is it's letting functions think that they're lines, right? Because again, if I zoom in enough, right, and my iPad won't let me go too much further in, right? But if you were to keep zooming in to this interval, this is looking more and more like a line, okay? And there's a natural connection here between the derivative and whether or not a function is increasing or decreasing. And that's the tangent line, right? Because notice, right, say I graph this tangent line, it's going to look something like that. Notice that if my function did think that it was a line at that point, right, the line it would think it was is the tangent line. And then since the derivative tells us the slope of the tangent line, Observe that if the slope of the tangent line is positive, our function is increasing. If the slope of the tangent line is negative, then our function is decreasing. Right? We have this situation here for this increasing function. I can just, throw a graph right down here. Say we have some function that's behaving like that. If I look at this point, it's going to have a tangent line like that. And this tangent line has negative slope, right? We can see that by just looking with our eyes, right? And because it has negative slope, the function is decreasing there, right? And this actually turns out to be a very important theorem when you're looking at the applications of the first derivative, right? We say we can sort of divide this into three parts, right? One, if my derivative is greater than 0, say if our derivative is greater than 0 for all x in some interval a, b, right? Then f is increasing. On AB. 2, right? If our derivative is negative for all x in AB, well, then f is decreasing. But notice here there's a third case, right? What happens if f prime of x equals 0? For all x in some interval, right? Well, and well, this part might take some thinking on your part to sort of reason through why this is the case. But it turns out that if f prime of x is constant, and I just realized that I used the if in f for both the letter f and my f prime. That should be a little bit better. Reason through all of these yourself, so that you're convinced that they're true, right? We're not going to prove this like most of the theorems in this course. But nonetheless, it is important, and we will be using this fact substantially, right? And we can do some examples with this, right? We can say, find where f of x equals x squared is increasing / decreasing, right? And where means finds the intervals where this is true. But we know that our derivative here is 2x, right? And then further, f prime of 0 is less than f prime of x is less than 0, sorry. When x is less than 0 and f prime of x is greater than 0, where x is greater than 0, right? So that means f is decreasing. F is decreasing on what interval? Well, f is decreasing when f prime of x is less than 0, which is when x is less than 0. So we're negative to 0. And by a similar strain of logic, f is then increasing on 0 to infinity. And then if we sort of think back and remember, right, the graph of a continuous function doesn't have any breaks in it, right? Therefore, it can't change sign, right, from negative to positive unless it equals 0 for some value of x. This is then going to tell us that if our derivative is continuous, we can use its zeros in order to determine where to look for these intervals, right? And so let's do an example of that, right? So let's say determine, what should we do for our function? Let's try x cubed minus 3x squared minus 24x plus 32, right? And we want to determine where that is increasing slash decreasing. And so we're looking for where it's increasing or decreasing, we should consider its derivative, which is what? It's going to be 3x squared, looks like minus 6x minus 24, right? You can factor a 3 out of that, and you're going to be left with x squared minus 2 minus 8. And that's then going to factor into x plus 2 and x minus 4, okay? And this is continuous everywhere, right? So our observation can apply, right? So we note that the zeros are x equals negative 2 and positive 4, right? So what that means, right, is I can draw this little line here, and I can put these important points on here, negative 2 and 4. And because our functions are continuous, right, this goes back to the intermediate value theorem, and these are where my function equals 0, the sign across each of these is going to be constant, right? This one isn't necessarily the same as this one, right? But on this entire interval, it's either, positive or negative, which means we can pick a single test point, right? Pick one test point that's, nice, and then we're good, right? Here we can say pick c equals 0, then f prime of c is going to be negative 24, right? So that means that this whole thing is going to be negative. Okay, well, what about here? Well, why don't we just pick, c equals 5, so it's not too big, right? And if we look at this, we're going to get 7 times 1, right, times 3. Or f prime of c is 21. So here we're positive, right? And then here for this last one, why don't we just choose c equals negative 3. And what's that going to be? Well, we're going to have, looks like negative 1 times negative 7. For 7 times 3 is once again 21. Okay, so then this is positive. So what that tells us, right, since it's 0 here, positive on this interval, negative on this interval, and then positive again here, well, that means f is increasing on what interval? Well, negative infinity to negative 2, union 4 to infinity, right? Because that's where our derivative is positive. Likewise, f is decreasing on -2 to 4, and it's neither increasing nor decreasing at -2 and at +4 because that's where our derivative equals 0. Let's take a look at another one, right? Let's say f of x, we're going to continue with the same sort of idea, right? So we'll say g of x is x to the 2/3, right? We're looking for where it's increasing and where it's decreasing. We see that its derivative, right, drop down the 2/3 and next to the -1/3. Now notice that f prime of x is going to be discontinuous at x equals 0, right? It's going to be continuous everywhere else, but at x equals 0, it's going to be discontinuous, which is unfortunate. But also notice that this isn't going to be equal to 0 anywhere, right? There's no way for this function to ever equal 0. So what that means is we actually still have a similar setup that we're going to be looking at, centered now around 0 because it's continuous all here and continuous all here, which means that once I find the value of some test point here, all of this is determined. And if I find the value of some test point here, all of this is determined, right? And I can pick the very natural, well, 1 and -1, right? Notice that if we choose c equals 1, we get g prime of c, sorry. That's going to be just 2/3, right? And so that means we're positive on this interval. And if we say choose c equals -1, we're going to get g prime of c. I guess it would be a little bit cleaner to write -1 in here. G prime of -1, well, -1 to the -1/3 is just -1. So we're left with -2/3, which means on this whole interval, we're negative, okay? And so then that's going to tell us what? So that means f is decreasing on -infinity to 0, and f is increasing on 0 to infinity, right? And our function is not defined at x equals 0, okay? So when our function is continuous everywhere but a point, right, we can still use this sort of same logic that we used here in order to find our values on these intervals, okay? Take a look at one more example before we kind of go on to our next subject, okay? And let's say h of x is, say, x plus 1 over x, right? If we take our derivative here, h prime of x, well, it's what? It's going to be 1 minus 1 over x squared. If you're looking for a common denominator, you can multiply this guy by x squared over x squared and get x squared minus 1 over x squared, okay? And now we're curious about sort of using the last two ideas. Where is h prime discontinuous? And where is it 0? Okay. So I guess, interesting points, we'll call them that. In the next part of this lecture, we'll give them their proper name. But here are the points that we've discovered are interesting. X equals 0 is going to be interesting because that's where this has a vertical asymptote and is, hence undefined. And then the zeros of this function, which are going to come from the zeros of the numerator, right? We're looking at plus or minus 1, okay? So now we can sort of pick this same sort of picture, right? We'll need 0, we'll need 1, and we'll need -1, right? And we'll pick some points, right? Maybe we'll pick 1/2, 2, -1/2, and -2, right? Those seem like, the most clear-cut way to do this. And then we can just start plugging these in. Starting with -2, right? We'll see h prime of -2. It looks like it's going to be 4 minus 1, or 3, over 2 squared, which is 4. Right, so we're going to be positive there. And then I'm going to actually take a second to note that h prime of 2 is going to be the same thing. Right? H prime of 2 is also 3 over 4. Right? Noticing that we're going to get 4 minus 1 for 3 over 4. So we're positive on each of those intervals, which is great. Now we need to calculate, we'll say start at plus 1/2. And I think it's actually going to be easier to look at it here, right? Because 1 over 1/2 squared is going to be 1 over 1/4, which is the same thing as 4, right? 1 over 4 is just 4. And so when we subtract 1 from that, we're going to see that h prime of 1/2 equals -3, right? And you can make a sort of symmetry argument, right? H prime of -1/2 is also going to be -3 because these squareds, or I guess this square, is going to remove all of our negatives, right? And here, just like that, with this, little number line, we've got our intervals. And I guess before I write those down, I'll remind us we have 0, 0. We have a does not exist there, right? And we can write down our conclusions, right? So f is going to be increasing on what? Well, -∞ to -2, union, -∞ to -1, union 1 to infinity, right? And f is decreasing on, it looks like -1 to 0, union 0, union 0 to 1, right? One thing to notice here, right, is it's not increasing or decreasing at 0, right? Because our derivative doesn't exist there. So we do need to take care to exclude 0 here. Another thing to notice here is that we can't just assume that it will always switch, right? The last two examples we had, across each of these boundaries, our derivative flipped signs. That isn't the case here, right? So we can't automatically conclude that just because your derivative is equal to 0 or it doesn't exist, doesn't mean that the sign is going to change, okay?